All right, let's summarize the fundamental quantities that we will deal with very frequently in these chapters and their units and the main equations that use them. We start with the three fundamental quantities: mass, time, and length or distance. Length and distance are basically the same. That have the units kilogram for mass, second for time, meter for distance or length. From the time and distance, we can define a derived quantity, which is the speed. Speed equals distance divided by time. And that's why it has a unit of meter per second, the unit of distance divided by the unit of time. And then in the context of light, we define light with either frequency, nu, or wavelength, lambda. The units for frequency, nu, is going to be second minus 1, or hertz. Those are the same thing. And wavelength, lambda, has a unit of meter because it's a distance or a length. Or typically, we use very short wavelengths, so we typically use it in nanometer range. The relationship between these two quantities is given by this equation right here, as the speed of light equals the product of lambda times nu. And then we have energy, which has a typical unit of joules. Most common form of energy that we typically calculate is kinetic energy, that is given by the equation energy equals half mass times the square of the velocity or the speed. It's a little bit confusing because velocity or speed has the symbol of v, which looks very similar to nu, that symbol for a frequency. So pay attention to this and don't get them mixed. In the context of light, energy is given by Planck's formula, which is energy equals h nu. H is Planck's constant. If you take the relationship between frequency and wavelengths into account, we could have an alternative for Planck's formula where energy equals hc over lambda. For the context of the atomic structure, the energy of the energy level is given by this equation here as negative 2.18 times 10 to negative 18 joules multiplied times 1 over the square of the principal quantum number n. And that's for hydrogen atom only. As we said, when we describe light, we could describe it with its frequency or with its wavelength. So if you have the wavelengths, you could calculate frequency and vice versa. So if you know that the wavelength lambda equals 325 nanometer, what would be the frequency? The first step is going to be wavelengths from nanometer to meter using SI prefix for nanometer, and it should be 3.25 times 10 to negative 7 meters. Second step is going to be rearranging the relationship between frequency and wavelengths to solve for frequency. So we start with the equation and rearrange it to solve for frequency nu. So nu is going to equal c over lambda. You just plug in the values. C is equals 2.99 times 10 to the power 8 meter per second, and divided by the wavelengths in meter that we calculated in the first step. And you find the frequency to be 9.23 times 10 to 14 second minus 1, or hertz. Sometimes the question probably would ask you to put the answer in a higher unit using the SI prefixes. So you could probably express this as a megahertz. So you will need to convert this from hertz to megahertz using the SI prefixes, which is 1 megahertz is 10 to the power 6 of hertz, is 9.23 times 10 to the power 8 megahertz.